Okay, let's now talk about the inter-process communication. And before I talk about the inter-process communication, let's see why communication. The idea behind having more than one process running concurrently or in parallel is, to reduce the waiting time, as you will see later, and many, many other reasons. But among those reasons is the ability for those processes to cooperate or collaborate. What does it mean? Imagine you have P1, P2. P2 already calculated the sum of numbers, okay, from 1 to 100, I. Okay, this is already calculated. So basically 1 plus 2 plus 3 until plus 100, okay? That's what it means. And for P1, it's doing some calculations, and part of this calculations is to get the sum from 1 to 100. The question here is, why reinvent the wheel? Okay, the sum from 1 to 100 is already calculated by P2. So instead of P1 recalculating this value again, it can actually reuse, okay, or use this value that P2 has already calculated. So this is what we call cooperation or collaboration, all right? But for this to happen, those two processes have to communicate. How will P1 request this sum and how P2 will provide this value? It has to have some kind of communication. Rule of thumb: there is no cooperation without communication. It doesn't happen. Okay, there is no cooperation without communication. That doesn't happen. Regardless how the cooperation works, that doesn't really make much difference, but there should be some kind of communication for it to cooperate. So processes within a system may be independent. What does it mean for it to be independent? A process does not depend on any other processes. That's not a good thing in computation, by the way. Okay? That is not a good thing. Dividing work into pieces that cooperate together is much better. For what? For many, many matrices that you will see later in this course, okay? So it could be independent or cooperative. Cooperative, they could be cooperating, as I mentioned in this example. Cooperating processes, okay, can affect or be affected by other processes. Of course, that's how it works. You need data from some process. You will be giving data to some process and so on. Okay. Reasons for cooperation, of course, information sharing. So you don't need to reinvent the wheel. Computation speed up, of course. Instead of having big sequential program, you can divide it into pieces, and those pieces can work concurrently or in parallel. Modularity, dividing this big program into modules. Independent, well, maybe independent is not the right word here in this context, but I mean separate modules. Okay, and those modules will communicate together. And convenience, in order, if you have a programmer or a software developer, it's always convenient to divide big projects into smaller modules that talk to each other rather than one big program. It's also for the maintenance, for bug fixes, for many other reasons. For the stability of the system, for many other reasons that is related to software engineering. So cooperating processes need inter-process communication. So it's a prerequisite for the cooperation to have communication. All right? We call this IPC. IPC. Inter-process communication. We can do the IPC through shared memory or message passing. So this is number one, shared memory, and then number two. What is shared memory? You have here process 1, you have process 2, and they want to communicate. You get shared memory between the two. So P1 can write in a piece, P2 read from that address. So P1 write in address 100, this example, P2 reads from address 100. So you pass the information from P1 to P2. Here is the communication. And then P2 responds back in address 200 as an example. And then P1 reads the response from 200. Here they are. P1 and P2 are talking. Okay? So this is shared memory. You have here shared memory between the two processes. Or message passing. So P1 and P2 are not going to be talking directly, but P1 has a mailbox here. I'll call it M1. And P2 has a mailbox. I'll call it M2. And P1 and P2 will send messages to each other. Okay? So this is the message. Of course, it doesn't have to be a mailbox, as you will see when we talk about the direct and indirect communication. Okay? But in the end of the day, here you have a shared memory. Okay? Like we are in class. Whatever I write on the board, okay, you guys will read. Okay? So we can communicate without talking by writing on the board. That's what happens here. Okay, and then one of you wants to respond back, they come and write on the board as well, and I read it. This is the shared memory between all of us. Or message passing, so we send each other messages. Okay, all right, now let's see how every model works. Here is process A, here is process B, and they have, do you see, shared memory. So process A writes in here, process B reads it, and then process B responds back, and process A reads it. Shared memory between A and B. Or you have messages. See here, the message queue. Here it is, messages. And those messages are being sent by one process and the other reads. Okay, so let's say M1 could be sent from A to B, so B will read it, and then B will respond by message N, so A will read it, and so on. Okay, you will see how this works. All right. One of the problems that explains the memory model or the communication in general is called producer-consumer. 3 problems, if you understand them, you know operating systems. The first one is called producer-consumer. This is the one I'm going to be explaining now. Reader, writer, and dining, my favorite philosophers. Producer, consumer, one is producing, one is consuming. Reader, writer, one is reading, one is writing. What is the difference? It looks the same. No, it's not. Here, reader writer, you have a single memory location, whereas producer consumer could be a whole buffer. Okay, it's a different problem. Dining philosophers, you have 5 or 6 or n philosophers sitting together on a round table like that, having dinner, and they will starve to death if they don't follow certain approach that you will learn later. Any problem in operating system can be classified as either producer consumer, reader writer, or dining philosophers. Okay. As an example, if you have an array, this array, one process writing in the array and the other one is reading from the array. Okay, so then it's a producer consumer. Okay, it's a producer consumer. You have a counter. And this counter, 2 processes are changing in this counter. Then it has a reader-writer problem. Okay. You have many processes that asking for resources to work. Then it's a dining philosopher. And so on and so forth. Any problem related to operating systems, related to computer system, can broadly be classified to be either producer, consumer, reader, writer, or dining philosophers. Having said that, it means if you know which paradigm the problem belongs to, is it a producer, consumer, is it a reader, writer, then you can solve it. Because we already have solutions for the producer consumer, we already have solutions for the reader writer, we already have solutions for the dining philosopher. So as soon as you classify the problem and you know which paradigm it belongs to, you will know how to solve the problem. Today I'm going to be introducing the very first problem, which is the producer consumer. So the producer process produces information, okay, that is consumed by a consumer, as you will see. We have 2 variations. The very first variation, we call it unbound buffer, okay, which places no particular limit on the size of the buffer. Okay, so there is no limit, as you know, unbound buffer, as I mentioned in the lecture, which means the producer will never wait. Okay, because it's unlimited. So why for the producer wait? The buffer is infinite. The producer P, the consumer C, here is the buffer. This buffer has no maximum limit. So this jar is big enough to take infinite number of objects. So the producer doesn't need to wait at all. The producer will always keep putting into this jar. Okay? The consumer waits until there is at least one item in the jar for it to consume. Of course. So that's the first variation. Okay? How about the bounded buffer? Bounded buffer means here is the producer again. Here is the consumer. This buffer has a maximum limit. Okay, let's say 100 locations, 1 billion locations. It doesn't matter how much, but you have a number that limits this size. Okay, so there is a maximum number of items that can be produced before getting consumed. Okay, in other words, you have here limited number of locations. Number of locations. In this case, the producer will keep producing until this buffer is full. When the buffer is full, the producer cannot produce anymore until the consumer consumes. Why? Because when the consumer consumes, you now have empty places. So the producer can produce again. Okay? Two problems related to the buffer. The first one is called overflow. And the second one is called underflow. The underflow is when the buffer is empty and the consumer is trying to consume. The overflow means when the buffer is full and the producer is trying to produce. Because if the producer produces, there is no place to put that production. Okay? If the buffer is empty, there's no place or there's no object in this buffer for the consumer to consume. So this is the underflow and this is the overflow. The overflow is the responsibility of the producer. Why? Because the producer is the one that puts items in. Whereas the underflow is the responsibility of the consumer. Why? Because the consumer is the one that takes objects out of this buffer. Okay? All right. So what is the buffer? An area of memory shared among the processes that wish to communicate. So you can have something shared between them. This is for the shared memory, IPC shared memory, okay? The communication is under the control of the users, okay, or the user processes. Not the operating system, but the user, as you will see in the code, okay? Here, not the operating system. Major issues is to provide mechanism. So it's very important to provide mechanism that will allow the user processes to synchronize. Why? I just mentioned the overflow and underflow problems. You are trying to avoid overflow and you're trying to avoid underflow. So you're trying to avoid the overflow and the underflow. Okay, the synchronization will be seen later, okay, in chapter 7. Look at this. Here is the bounded buffer. We can always define it this way in C. In C, you can always define any value like that, by the way. Define. I know most of the people don't like C, but C is a beautiful language. It's the base of any other language. Even Python is created by C, by the way. It's written in C. Buffer size of 10. Okay? So what does it mean? When in the code, when you see the word buffer size, you can always replace it with number 10. Okay? Then we're going to be defining a struct. If you don't remember the struct, a struct is a combination of certain variables with their types put into one unit together. This unit is called item. For this code, we don't care what the struct is defined by. It doesn't matter. It could be an elephant, it could be a car, it could be a number, integer, a float, a double, a spaceship. It doesn't matter. We don't care. Okay, it's just an item for us. So what is the buffer? It's an array. The size is buffer size. What does it mean? 10. Of type item. What does it mean? You have an array like that. This array has location 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it. Why? Because it's 10 locations from 0 to 9. Okay? And we have here two variables that we're going to be using. The first one is called in, and the first one is called out. All right? Here, in this case, we will be using the buffer as circular. How are we going to be bending the array to be circular? You will see it in the code by taking what we call mod. Here. So this is location 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Look at that. Just explanation so you understand what you're going to be seeing in the code. Here is in. In is initially 0, and out is initially also 0. Okay. What is in? In is the location where you want to produce. Okay? So the next place to produce. Which is initially, what you're going to be producing, What is the out? The location of the object that you want to consume. So in is controlled by the producer, because in is the location where the producer will put the production. Out is controlled by the consumer, because it's the location the consumer will take the object from to be consumed. All right? Now, imagine this scenario. The in, you produced one item, now in is here. You produced another item, in is here. You produced another one, here, until, look, you produced here, and then you produced here. The next production should be at location 0. If the object here has been consumed. If the object has been consumed. Okay, as you will see in the code. So how would you do that? Okay, how is the 10 when you say in equal in plus 1? So when it was 0, it became 1. Yeah, substitute n equals 0. So n equal 0 plus 1, it became 1. Perfect. And then add 1 again. N equal 1, because it became 1 plus 1, it became 2, and so on. How, when I reach a 9, I say n equal 9 plus 1, it becomes a 0 again. How is this possible? Simple. N equal n plus 1 mod 10. Why 10? Because you have 10 locations. What if you had 15 locations? Mod 15. What if you have 21 locations? Mod 21. What if you have 3 locations? Mod 3. What if you have 3 million locations? Mod 3 million. What if you have buffer size? Buffer size, then it is mod buffer size. So here is going to be n equal n plus 1 mod buffer size. Okay? All right. That will turn the array to be circular. You have studied that in data structure. Okay, when we talked about hashing, if you remember. All right. Now, here is the code. Here is the production. We have item next produced. While true, this is an infinite loop. And then look at that. While n plus 1, We know now why we say mod buffer size. So it's circular. Equal out. What is this scenario? Here it is. Look. Here is the buffer. Here is the out. So this has an object to be produced. Oh, sorry, that has been produced and it needs to be consumed. And it's not consumed yet. And the producer kept producing until n is here. So who is n plus 1? The out. Now if we produce again here without this being consumed, you overwrote it. It's gone. It's lost. So as soon as you reach here, you have to stop until the consumer takes the object out. Now this place is empty. You can add to it. So how is this condition happening? While n plus 1 equal out, here is the situation. Look, if the next step is out, there is something here that you shouldn't overwrite. So wait where you are. How would I say wait where you are? Semicolon. Here it is. C. Okay. Why am I saying mod buffer size? Because of the circle. I mentioned it before because of the circle. Then, if this is not the case, now you can produce. Look, buffer of n equal next production or produce, and then add, n equal n plus 1 mod buffer. Okay, so you added with 1. All right, now this is the production, and so the producer. If you understand this, the consumer is much easier. Look, again here, I said n points at the one to be produced, the one to be produced. So here it is. So here is the out. If out is in, it means this is the next production location. So you cannot consume anything because it's empty. So if the in is out, do nothing, it's semicolon, and then if it's not, consume and move the out one more location. That's the producer, consumer. In order to understand this code and the other one, you have to imagine that the producer and the consumer are working in parallel. So you should ask, okay, you know what? If this equation will equals out, it will always equal out in the producer. No. Why not? Because the out is being changed in the consumer. Which means, by the way, that the buffer, the in and out, are shared between the producer and consumer. The same variables, which I will show you how to do it. Okay, we'll continue in the next video.